Welcome to the continuation lecture on calorific value. In the earlier videos, we had discussed about the calorific value and types of calorific value. Later we had discussed about the determination of calorific value using Dulong formula. Now we will discuss the practical determination of calorific value. So now practically or experimentally the calorific value can be determined using 3 calorimeters: Junker's calorimeter, Boyle's gas calorimeter, bomb calorimeter. Junker's calorimeter is used to determine calorific value of gaseous fuels and liquid fuels that can be easily vaporized. By using Boyle's gas calorimeter also, we can determine the calorific value of gaseous fuels and easily vaporized liquid fuels. And this bomb calorimeter is used to determine the calorific value of solid and liquid fuels. Now coming to the first calorimeter, Junker's calorimeter. As earlier I have said, this Junker's calorimeter is used to determine the calorific value of gaseous fuels and easily vaporized liquid fuels. So this is the Junker's calorimeter. So this Junker's calorimeter consists of this one. This is called as Bunsen burner. Gasometer, thermometers T1 and T2, and this is the annular space for water, and this is the outer one, which is chromium plated outer jacket. Coming to the construction of Junker's calorimeter. Junker's calorimeter mainly consists of a vertical cylinder combustion chamber. Here, the burning of gaseous fuels is regulated with the help of the Bunsen burner, which is clamped at the bottom. And this combustion chamber is surrounded by annular space for water, and not only for that, for interchange of coils. And this is again surrounded by an outer jacket which is chromium plated for preventing the radiation and convective loss of heat from calorimeter. So this radiation and convective loss of heat from calorimeter is prevented by this outer jacket. And there are openings for keeping the thermometers. Here this is an opening for keeping the thermometer and this is another opening for keeping another thermometer. These thermometers are kept for measuring the temperature of incoming water and outgoing water. And here the fuel that is being burnt in the calorimeter will be regulated by the gasometer. This is about the construction of Junker's calorimeter. Now coming to the working. In this calorimeter, a known amount of fuel is burnt in excess of air in such a way that the heat produced due to combustion of this gas will be absorbed by the water flowing here. And here water will be flowed at a constant rate. Next, the temperature of the incoming water. So this T1 thermometer is set for what? For measuring the incoming water temperature. And this T2 is meant for measuring the outgoing water temperature. At the same time, we have to note down the weight of the water that is flowing in time t. By measuring all these values, we can determine the calorific value as follows. Calculations. Let V be the volume of gas burnt in time t at STP. Let W be the weight of water collected in time t. T1 be the temperature of incoming water T2 be the temperature of outgoing water. From this, HCV can be calculated as HCV is equal to W into T2 minus T1 by V kilocalorie per meter cube. Suppose if M is the mass of steam condensed in graduated cylinder, that means V meter cube, then LCV can be calculated using the formula LCV is equal to HCV minus M by V into latent heat of steam, that is 587 kilocalorie per meter cube. Using this formula, we can calculate the calorific value of a gaseous fuel or easily vaporized liquid fuels using Junker's calorimeter. Next, we will discuss about Boyle's gas calorimeter. Like Junker's calorimeter, this Boyle's gas calorimeter is also used to determine the calorific value of gaseous fuels and easily vaporized liquid fuels. So this Boyle's gas calorimeter mainly consists of a burner, this is an insulated one, the entire apparatus will be insulated, and these are the thermometers which are arranged, and this is the opening for water inlet. And from the top water will be going out, and the products of combustion will be condensed, and this shows the steam condensed as water. Now coming to the construction of this Boyle's gas calorimeter. Boyle's gas calorimeter consists of a suitable burner, and here known volume of gas will be burnt at known pressure at constant rate. This burner is enclosed with a or surrounded by a combustion chamber. Burner is surrounded by combustion chamber. See here, this is the combustion chamber which consists of copper coiled tubing. So this is the inner copper coil and this is the outer copper coil through which water will be flowing. Now the water will be flowing at a constant rate. First, water enters into outer copper coil next through inner copper coil and exit at the top. Here the thermometers T1 and T2. T1 will measure the temperature of incoming water and T2 will measure the temperature of outgoing water. So this is about the construction. Now coming to the working. Here the fuel will be burnt in the combustion chamber. At the same time, water will be allowed to flow through it for 15 minutes. That means burning of fuel, that means burning of gas and water flow. This will be continued for 15 minutes so that calorimeter will warm up. When once the calorimeter is warmed up, then the burning of the fuel and water supply should be carried in such a way that water will be going at the top at atmospheric pressure. During that time, we have to measure T1 and T2, that means temperature of incoming water and temperature of outgoing water. At the same time, we have to record the weight of water collected in during this time and the amount of steam that is being condensed by passing through the cooling system, and that weight should also be calculated or measured for determining the LCV. Coming to the calculation. Let V be the volume of gas burnt in time t at STP, and W be the weight of water collected at time t. L be the high calorific value. T1 be the temperature of incoming water. And T2 be the temperature of outgoing water. Then heat produced due to burning of fuel or gas is equal to VL. Heat absorbed by water is equal to W into T2 minus T1. From this, heat loss is equal to heat gain. That means we can write it as VL is equal to W into T2 minus T1. implies L is equal to W by V into T2 minus T1 kilocalorie per meter cube. This is how we will be calculating the high calorific value using Boyle's calorimeter. Now calculation of LCV. LCV is equal to gross calorific value L minus W dash by V into T2 minus T1. Sorry, it's not T2 minus T1, it is latent heat of steam. Here W is the weight of water that has been condensed. Implies LCV is equal to L minus W dash by V into 587 kilocalorie per meter cube. Now we will be doing a problem on calorific value using this formula. So see here, the problem is in Boyle's gas calorimeter, following data were recorded. Volume of gas used is 0.1 meter cube at STP. Weight of water heated is 20 kg. Inlet water temperature is 20 degrees centigrade. Outlet water temperature is equal to 35 degrees centigrade. And weight of steam condensed is 0.2 kgs. Find the higher and lower calorific values per cubic meter at STP, considering that heat liberated in condensing water vapor and cooling the condensate is 580 kilocalorie per kilogram. So this is the problem given to you. Now coming to the solution. So first of all we will write the given data. Given data is volume of gas used. Volume of gas used V is equal to 0.1 meter cube at STP. Weight of water, that is W is equal to 20 kgs. Next, inlet water temperature. Inlet water temperature T1 is equal to 20 degrees centigrade. Next one is outlet water temperature. T2 is 35 degrees centigrade. Weight of water condensed. W dash is equal to 0.02 kgs. Next given, latent heat of steam. Is 580 kilocalorie per kilogram. So this is the data given to us. Now first we have to calculate the higher calorific value. Higher calorific value means L. The formula given to us is L is equal to W into T2 minus T1 by V. Here L means high calorific value. So what is the value of W we have here? 20 into T2 is 35, T1 is 20 degrees centigrade by volume of gas is 0.1 meter cube. By simplifying all these, we will be getting 3000 kilocalorie per meter cube. This is the higher calorific value of the given fuel. Now LCV. The formula for LCV is HCV minus M by V into latent heat of steam. Here this M is nothing but the weight of water that is condensed. That means this we can write it as what? W dash. So this will be equal to HCV 3000 kilocalorie per meter cube minus the W dash value is given as 0.02 by 0.1. Latent heat of steam is in general we will be taking 587 kilocalorie per kilogram, but it is given as 580 kilocalorie per kilogram for this fuel. 580. Simplifying this, 3000 minus 116 is equal to 2884 kilocalorie per meter cube. So this is the lower calorific value of the given gaseous fuel. In the next video, we will discuss about the determination of calorific value using bomb calorimeter. Thank you.